Well, welcome to this online revision session for AQA FP3, which we're looking at the January 2011 question 7 on Maclaurin expansions and then its application to finding a limit. You can see in part A of this question we'll just be using the definitions given in the formula booklet to write the expansions. Second part we'll be finding an expansion for e to the tan x and being led through to the result for that one. And then finally in part C we have an expression for which we're going to find the limit as x tends to 0. So the first part of the question, fairly straightforward. These are the definitions given in the formula booklet, and so we can apply those to our parts to this question. So we've got cos x plus sin x. So we have cos x as 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial. Sin x as x minus x cubed over 3 factorial plus x to the 5 over 5 factorial. Notice we only need to go up to the x cubed term, so we only need the first two terms from each of these expansions in order to get our result. So if we add those together we get 1 plus x minus x squared over 2 factorial minus x cubed over 3 factorial, and then all the other terms beyond that we're ignoring at this point. Similarly, to get ln of 1 plus 3x, we're replacing x with 3x in the expansion of ln 1 plus x. So substituting in 3x into this expansion, and the first three terms that we require will give us 3x minus 3x all squared over 2 plus 3x all cubed over 3, which if we tidied that up will give us 3x minus 9 over 2 x squared plus, well, 3 cubes, 27 over 3 takes you back to 9, so this is just 9x cubed. Okay, there's only 2 marks for this, so for getting the first one correct you'll just get 1 mark for stating that accurately, and then 1 mark for stating the result for the ln. Part B, we're now going to apply the Maclaurin expansion to actually work out y equals e to the tan x. So in part 1 we're being asked to find dy by dx. In order to get that one, it's e to the something, so we know differential of e to the something is e to the something, but then we've got to differentiate tan, which gives us sec squared, so this becomes sec squared x e to the tan x. And then we've got to find the second differential, so if we differentiate both sides we can see now we have a product, so the differential of sec squared is going to become twice sec tan x and that's multiplied by e to the tan x. And then we're going to differentiate the e to the tan x and multiply it by sec squared. Well, the e to the tan x was sec squared e to the tan x, so that becomes plus sec to the power of 4 x e to the tan x. Now we've got to look to get the result that they've got, which we've got to show that it's equal to 1 plus tan x all squared times dy by dx. Well, dy by dx is sec squared e to the tan x, so we need to take out a factor of sec squared out of both sides, and if we're going to do that, we're going to end up, and just looking through this I realised that I dropped a sec, haven't I, because here we were differentiating sec squared, so it becomes twice sec, but then you've got to differentiate sec, which is sec tan, so this should then become twice sec squared tan x. Going to have trouble getting the sec squared out as a factor otherwise. So if we take out the sec squared x e to the tan x, and then we are left with twice tan x plus sec squared. And so we can see that this part here, the sec squared e to the tan x, is dy by dx. And then we know that sec squared is 1 plus tan squared, so if you've got 1 plus tan squared plus 2 tan x, then this will then become the 1 plus tan x all squared. Part 2, we've then got to find the value of d3y dx to the power of 3. And where's the third differential? Yeah, much nicer way of saying it, wouldn't it? Okay, and so we've got to differentiate this expression again, so we can write down the fact that the third differential is equal to differential of the first part, which becomes d2y by dx squared, times 1 plus tan x squared, plus leave the first part alone, and then differentiate the 1 plus tan x, which is going to give you two lots of 1 plus tan x multiplied by the differential of tan, which is sec squared x. So to find the value of this, we need to know the value of dy by dx and d2y by dx squared. Well, we know dy by dx is equal to sec squared x e to the tan x. So sec is 1 over cos, which means that when x is 0, that becomes 1. Tan of 0 is 1, so the whole thing is 1. So we know that dy by dx will be equal to 1. This is when x is equal to 0. And similarly, the second differential will be equal to 1 plus tan x squared. Again, tan of 0 is 0, so that's 1 squared. Dy by dx was 1, so this is still 1. And so if you substitute all of those into here, we've got 1 squared plus 1 times 2 times 1 again, and sec squared is also 1. So that gives you a total of 3. So now we can use Maclaurin's expansion to find y as an expansion. So it's the function evaluated at 0, so tan of 0 is 0, e to the 0 is 1, plus it's the first differential evaluated at 1 times x, plus the second differential evaluated at 0 over 2 factorial times x squared, and then it's the third differential evaluated at 0 over 3 factorial times x cubed, which gives us our result of 1 plus x plus x squared over 2 plus x cubed over 2. That's the 3 over 6 from the 3 factorial there. Okay, as to where we get the marks again here, we're going to get a method mark and an answer mark using the chain rule here to give us 2 marks, and then a method mark here specifically to do with applying the product rule, and then an answer mark for obtaining this result. This result here, and then 1 for then tidying it up into the form that we require. For evaluating the third differential, again we'll get 1 mark for the correct differentiation, and then 1 mark for evaluating it correctly, and then finally for them knowing what all the various differentials are and applying that into the expansion and getting the correct result will give us our final 2 marks in this part of the question. Finally, we're then looking for this limit, so we're going to substitute in all the expansions that we know to start with. So we're going to get the limit as x tends to 0 of try and put a straight line on here somewhere would be good. Okay, so on the top, what do we have? We've got e to the tan x, which is the 1 plus x plus x squared over 2 plus the x cubed over 3, and then we're subtracting the 1 plus x minus a half x squared, sorry, that was a half x squared minus the 6th x cubed. And then on the bottom we've got x multiplied by expansion for the ln function, which was 3x minus 9 over 2x squared plus the 9 over 9 lots of x cubed. Okay, now before we can take that limit we need to consider what we're going to divide by and simplify. Now we can see we've got a 1 there and a minus 1 there, and we got an x there and a minus x there, both of which will disappear. So on the top we are now left with what are we going to have? Well, we're left with a half of x squared minus another half of x squared, so that leaves us with a whole x squared, and then we got a third of x cubed minus a 6, so a third plus a sixth is a half of x cubed. And on the bottom we've got 3 lots of x squared minus 9 over 2 x cubed. And we're really not going to be worried about those next terms because they're going to be higher powers of x. So if you remember now, the trick is to give you at least a constant term in the beginning. So if we divide top and bottom, in this case, by x squared, that will give us sorry about that line. It's going to give us 1 plus x over 2, and then we're going to have other values of x squared, x cubed, and so on, and on the bottom we're going to have 3 minus 9 over 2x and other terms, and so on. And so in conclusion to the question, if you now let x tend to 0, you're going to have 1, this term will disappear towards 0, this term here disappears towards 0, so you just got a 3 on the bottom, and so the limit as x tends to 0 is 1/3. In 3 marks for this part. Initially 1 mark for using all the correct substitutions in here, and then the technique of simplifying this down into the appropriate form gives you a mark, and then 1 mark for stating or obtaining the correct limit at the end of that process. Well, hopefully you found that works solution helpful. For more help with your maths revision, please go to the Further Maths Support Programme website.